Hello, everyone. I hope you can hear me okay. Welcome to this afternoon's Nodes 2025 Data Intelligence session on enhancing benefit adjudication through graph node embedding, clustering, and outlier detection. We are the graph team from Amida Technology Solutions. I'm Manish Mithwal. I'll be the presenter. We're going to cover how a hospitalization benefit adjudication process can be improved with graph data science techniques. Our goal is to capture complexities and to reveal patterns and nuances in data sets that would otherwise be difficult using conventional analysis techniques. We demonstrate how graph node embeddings, followed by clustering, identifies outliers in the graph, outliers. Of course, high quality data is a key for any AI or ML work, but in healthcare, it's especially important. We often see issues like duplicate patients, inconsistent claims, or clinical combinations that don't line up. For example, when a patient ends up in a benefit group that doesn't make sense based on their history. These kinds of problems are subtle, and they sometimes slip through traditional cleaning methods and can be detrimental to downstream in AI and ML models. To catch them, we need to understand the relationships in the data. Our graph team has built a repeatable, scalable approach that uses unsupervised graph techniques to help us improve data quality, resolve hidden inconsistencies, and uncover meaningful patterns. In this presentation, we're going to apply this approach to a hospitalization benefit scenario. When someone is admitted as an inpatient, it can affect their eligibility for expanded benefits. Our graph approach helps group related hospitalizations and flag ones that don't fit the pattern so we can avoid training models on bad data. We hope that our approach to outlier detection leads not only to better AI and ML models in general, but to improved patient outcomes overall. Here, I want to give a technical overview of the AI decision support program that we have. It's a 5-step process. We start by taking exemplar patient healthcare data and convert it to a graph. We generate embeddings, which are a numerical representation of the graph data. We can then cluster the embeddings and identify clusters which represent validated data because they can be used for training because the outcomes are similar, and outlier data that indicate dubious or unreliable data. This ability to create a unique view of similarity of benefit decisions will help highlight patterns in the data that are otherwise not apparent. Ultimately, the enhanced data sets that result from this process will allow us to train AI and ML models that are used for improved patient outcomes. Let's look at this approach from a topological perspective. We start from clustered tables, things like hospitalizations, diagnoses, and procedures, and convert them into a graph. The graph perspective allows us to view what is related and how directly. Taking this a step further, we transform the graph into nodes and into points in a multi-dimensional space. This lets us see how nodes relate to each other, not just the direct links, but also the deeper patterns. We can spot records that cluster together, which ones are similar, and which ones stand out as outliers. Even when the data is messy or sparse, this structure is helpful. It supports classification, surfaces high-quality records, and lets us measure distance between nodes in a complicated graph. Those steps that we just outlined are only one part of our entire program. Though our immediate task is to use embeddings to be able to discriminate good training data from bad training data, the subtext is that the graph point of view enables a unique and often improved view of the data. Additionally, we want to be able to have a template that we can apply to new use cases. Ultimately, this can have a broad impact on a variety of uses, from enhanced data integrity, improved productivity, and better decision-making. At the core of our procedure is the graph data model. A graph data model has significant advantages over a relational model since it provides a natural representation of real-world problems. It's very flexible, and new data from disparate and inhomogeneous data sources can be incorporated. And as we will demonstrate, it allows us to find similarities in the data, which is the key to our program. This diagram here to the right is the data model that we will be using for this presentation. At the center is a patient node shown in light blue. Other data relevant to our use case is benefit in dark blue, diagnosis in red, medication in yellow, and age bucket, which is a range of ages that a patient falls into in green. In order to demonstrate our clustering and outlier detection methodology, we constructed a synthetic data set that adheres to the data model just described. For each benefit category, there are approximately 75 patients, each associated with a set of medications and diagnoses. Additionally, each node can have multiple properties. Here, for example, each patient can be associated with a benefit node type, which in our example is asthma, PTSD, panic disorder. There's a fourth group that has medications and diagnoses with no particular pattern associated with a benefit to serve as an outlier group, and importantly, is also a source of noise. Here is a closer look at the patient medical data set that we'll be using to demonstrate our program. There are 3 patient cohorts of approximately 75 patients that can have one of the 3 conditions that we just outlined earlier: asthma, PTSD, and panic disorder. Each medical condition is associated with a set of drugs and a code from the International Classification of Diseases, or ICD code. The fourth control group is associated with an additional 44 medications and 34 ICD codes. Actually, the graph that we previewed earlier is the entire data set that we're going to use. Each cluster that you see here to the top, bottom, right, and left corresponds to one of the groups that we just described here. For this particular project, we are using Neo4j, benefiting from its native graph storage and graph data science library. Here's an overall summary of the main categories of graph algorithms and models available within the GDS library. For our use case of finding similar cohorts of patients, we'll be using the Node2Vec and GraphSAGE embedding algorithms, both of which are available in the GDS library. As we will cover later, graph embeddings translate nodes or edges or subgraphs into numerical values that can be directly used as features for other machine learning tasks. Additionally, as we will see, similarity measures, in particular cosine similarity, can be used to determine outliers. To support the graph analysis, we built a pipeline that works at scale in Azure Cloud. We started Databricks, where we can take advantage of the Spark and Neo4j connector for writing and reading to and from a Neo4j database. The notebooks in our pipeline read data from a container in Azure Data Lake Storage. From there, data is loaded into Neo4j, where we define the graph structure, store the nodes and relationships. We can generate embeddings using one of the graph algorithms that we just talked about from the Graph Data Science Library, and then analyze them in the results in Databricks for clustering and anomaly detection. Any final data sets that we need, cleanup anomalies or other artifacts such as clusters or outliers, can be written back to cloud storage as we would like. With those preliminaries, let's take a closer look at the graph embeddings that we've talked about. Graph embeddings are meant to represent the graph as numerical data, which can be used to determine similarity and can also be used in clustering. The diagram to the right is a small example graph that adheres to the data model that we talked about earlier. There are the 3 patient nodes here in light blue, connected to medications in the yellow, diagnosis here in the red, and a benefit node. If we were to rearrange this graph into a flattened view that allows us to visualize patient similarity, here we would see that patients 1 and 2 share many medications as well as an ICD code, whereas patients 2 and 3 share fewer nodes. Ultimately, what we want from the graph embedding is that it should capture this general idea, this general pattern of what patient node is similar to other patient nodes. Okay, great. So how do you actually create an embedding? The first algorithm we are going to focus on is Node2Vec. Node2Vec only uses the graph topology to create embeddings, meaning that it only considers how nodes are connected. By simulating random walks within a graph, we can capture both the local structure of the graph as well as global structure of the graph by having walks that are near or far away from the starting node. These 2 here are a couple of example walks that could happen in our example graph that we talked about earlier. Additionally associated with each walk is a set of target and context pairs That is actually what is fed into the neural network used to train the embeddings. A couple of things to note for this. This algorithm is closely related to the skip-gram model in the word-to-vec algorithm in NLP that is used to generate word embeddings. We also note that this algorithm is transductive. If new nodes are added or updated in the graph, the model needs to be retrained to get new embeddings. This is important to consider in real-world cases where the data could be updated regularly and model training can be prohibitive. The other embedding algorithm we're going to use is GraphSAGE. SAGE is an abbreviation for sample and aggregate. GraphSAGE learns a function that generates an embedding based on the node's local neighborhood and features. The features of the sample neighborhoods are aggregated into a single vector. This aggregation is done by taking the mean or with pooling, and that choice can greatly affect performance. You can then see here an important difference between the two algorithms that we're using, GraphSAGE, and that GraphSAGE requires you to use node attributes, whereas node-to-vec did not. It only depended on the graph topology. That being the case, that makes this algorithm inductive, meaning that embeddings can be created for new nodes because the embedding for the node is determined by a learn function rather than having to train on the entire graph again. So we've just covered two algorithms that would allow us to generate node embeddings. However, it is the cosine similarity between embeddings that serves as a powerful metric to evaluate the relation between two different nodes. As a gentle reminder, the cosine similarity, the angle between two vectors, ranges from -1 to 1. When two vectors or embeddings are similar, the cosine of the angle is nearer to 1, and dissimilar embeddings have a value that is much less than 1 but greater than -1. Okay, now we have introduced all the tools that we need to evaluate the results from the embeddings we generated from node-to-vec and GraphSAGE on our entire sample data set. Using the embeddings created by node-to-vec, we can examine the similarity among patients. This diagram on the right is the affinity matrix of cosine similarity between patients. The patients have the same ordering on both axes, and the patients are sorted by their benefit. Each pixel in the heat map is the cosine similarity between two different patients. One again represents patients that have a high similarity, and 0, the lowest similarity. Clearly, the pattern shows that patients that have the same benefit have a high degree of similarity as compared to patients that have other benefits. It should also be clear just by seeing this pattern that similarity based on embeddings represent the similarity that we expect to see among patients across the three different groups. Here we have a heat map of patients versus patients using GraphSAGE. Generally, we see the very same pattern that we just saw from the node-to-vec embeddings. The heat map shows that patients that have the same benefit have a higher degree of similarity in the light color as compared to patients that have another benefit, the dark colors. As discussed earlier, GraphSAGE is not strictly relying on the topology of the graph, but rather uses a one-hot encoding of representation of the medication ICD codes and age ranges that we introduced in our data model earlier. If we switch focus a second from looking at similarity to detecting outliers, or let's switch focus. Density-based clustering is a type of unsupervised machine learning algorithm that groups data points into clusters based on their density and proximity to each other. The basic idea behind density-based clustering is to identify areas of high density and then group the data points together that are part of those dense regions. The table shows the clusters using the node-to-vec embeddings that we just previously saw. For this set of parameters, the clustering algorithm identified several clusters for each benefit group. But more importantly, the algorithm found data points that didn't fit into any clusters. We have labeled these as not clustered. These can be labeled as or considered as outliers. The embedding followed by clustering allowed us to identify nearly all of the 75 patients that were not associated with 3 benefit groups. These nodes can be considered ineligible and deficient to be used in an AI or ML training set. Here we take another look at the clusters formed by the embeddings. 2 figures show a 2-dimensional T/E projection of the embedding vectors. On the left is the projection of all the patient's embedding vectors. On the right is the projection, but with the patients labeled as outliers that we found from our clustering algorithms removed. Thus, after clustering the patient embeddings and identifying outliers, we see in the projection that our procedure has removed the noisy patient data that wasn't associated with the well-defined benefits. So putting it all together, remember our initial goal of the synthetic data set was to test the various algorithms and determine if embeddings could identify similar patients by their medical data, and also to validate that outliers can be found, that outlier data can be found in relation to the clusters. The results are clear. It worked. We have already applied our procedure to real-world data sets. In the future, as we progress, we hope to improve our embedding training procedures by using improved loss functions specifically for these use cases, incorporating other engineered features like centrality or community measures, or even possibly use the results from other work like ICD-10 embeddings for diagnosis instead of the one-hot encodings that we used here. Thank you for your attention.